right, the final speaker of this session is Arun Moorthy, who was a grad student here back in the roaring 90s. He finished an MS degree here in 1999, and since leaving us, he's been with several companies, Intel, Nexus Systems, Microsoft, and Facebook, where he's now the engineering manager on Facebook's network team. And that's what we're going to hear about today. So
thanks, Jim.
Take it away.
Anybody here did Jim's Comp 202 back in the day? Hey, David. I think you'll probably remember this. One of the most vivid memories I have of UNC, of Jim in particular, is we had these classes really early in the morning, right? Well, early for a grad student. It was like 9 o'clock. And Jim's always has a bounce in his step, but on this particular day, he walks in with a particular bounce, and he goes, "Two things happened which makes life infinitely better." Words to that effect. Election season's over, so no more ads on TV. And the X-Files, the new season begins. So as Jim mentioned, I was here in UNC for my master's after college in India. I collaborated with research with Kevin and Don, and Jim is part of the distributed and real-time systems group. I was I think Michelle and David from the group were in the room. And I used to hack on the BSD, free BSD kernel, working on the scheduler and the networking stack. And currently I manage part of the networking team at Facebook, focusing on load balancing and transport security. And I've been at a few other places, and with interests that have generally been in the space of networking, distributed system security, runtime environments. And probably the thing that ties together all of these places is almost all the systems that I worked on is in some form out in the public domain, even the stuff that I worked on at Microsoft. So what's in store today? We're going to peek inside Facebook's networking infrastructure. We'll try to see why this is a hard problem, and then we'll look at some aspects of the solution, both hardware and software, both in, on the edge and in data centers. And then we'll see what's next and talk about some, actually I want to hear more about what some opportunities for collaboration and partnership to take this forward would be. I made my best guess as to the technical details in here, but it's really what you want to see. If it's more than or less than or what you wanted to see here, let me know and we can tailor the presentation as appropriate. And stop me with questions along the way. I'm terrible at public speaking. I'd rather do conversation. So what are the challenges for Facebook's network? We're a social network, ever-expanding user base. Last time we checked, it was somewhere around 1.4 billion and counting. They generate a lot of traffic. The numbers here, full disclosure, I'm sandbagging a bit. These are the numbers that I'm allowed to disclose, but you can extrapolate from this if you want. We generate over 1 terabit per second of traffic through users generating over 10 million requests per second, or RPS. Different kinds of content gets handled. Video is one of the big content types we handle. We handle over 4 billion videos per day. And our user base is distributed across the world. More than 80% of our users come from outside the US and Canada. And all of this needs to be done highly available, highly reliable way. When Facebook goes down, people call the cops. This is a true incident from sometime last year when we had one of our biggest outages in recent times. People were calling 911 to wonder what's going on. This is from the LA, I think it's one of the Southern California Police Department's Twitter feeds. I kid, but in all seriousness, a lot of people use Facebook for many important things in their lives. And when it goes down, it affects them really badly. And we try really hard not to let that happen. Examples might be like coordinating relief efforts during disasters. Facebook use that for, people use Facebook for communications a lot during things like that. Let's start with a primer on what Facebook's global networking map looks like. We have data centers across the US and in Europe. These are large facilities the size of several football fields. They consume tens of megawatts of power. Everything in there is custom designed for us, by us. software, networking equipment, servers, the works. We also have what are called edge points of presence, or POPs, across the world. These try to bring the network closer to the user, and we'll see more about this in just a second. These are much smaller facilities, typically co-location facilities where we rent spaces, secure cages with racks, commodity hardware, servers, and networking equipment that we buy from vendors, running Facebook software. Much smaller footprint, maybe consume tens of kilowatts of power. Often I get asked, why do we need an edge network? Now, this map is a map of the latency. This is actually round trip time, so twice the latency, from different parts of the world to Facebook's data centers back in 2011. If the numbers are hard to read, darker is bad, and it goes up to about 800 milliseconds. 800 milliseconds might not seem like much, but remember that a page load can take multiple requests. And this is not an acceptable picture for us because our user base is distributed across the world. We want it to be lighter throughout the world. So to elaborate on latency, let's imagine a Facebook user, Mr. Bunny, in Seoul, Korea, trying to connect to one of our data centers. And the latency one way is 75 milliseconds. So your TCP or your round trip time is about 150 milliseconds. When the person connects, there's initially a TCP handshake, and that takes up a round trip time. Almost all traffic on Facebook goes over TLS, and that's another 2 round trips for that handshake to complete. And this is when they actually get to send their first packet of real data, or a request out to us. 4 round trips, 600 milliseconds before they get that first bite of that cute picture of that kitten. Kittens need to get delivered faster. And that's why we introduced the edge. So let's see what happens when we have an edge point of presence, a POP, located in Japan. NRT is just the airport code for Tokyo Narita. The initial connection happens from the user to the edge, and then the edge forwards the connection on to the data center. So the first half, the initial part is much the same. You still have a TCP and SSL handshake, but now it's between Seoul and Japan, and it's 15 milliseconds of latency. So you're done with your handshakes in about 90 milliseconds. When the user sends the request out, it gets terminated through a proxy at the edge. The proxy has long-running TCP connections from the edge to the data center. So you eliminate the overhead of the handshake on a per connection basis. So your overall latency gets reduced a lot. And this elaborates how why the principle of termination on the edge in general leads to lower latency. This is a fairly standard practice in the industry. This is why almost everybody has a presence on the edge. Now, we've been talking about dynamic requests, where a request needs to come into the data center where there's processing on the back end, which delivers content back to the users. The similar advantages also apply when you have static content. Static content is anything that can be cached: images, pictures, videos, JavaScript, CSS, anything that doesn't need computation on the back end. So imagine a request coming into one of our POPs. Taking it a level deeper, it hits one of our switches, which distributes the load across a collection of layer 4 load balancers. And all the boxes, other than the switch, are just commodity hardware running software that we built. So the layer 4 load balancer is a piece of software either we built or using kernel technologies like IPVS. The layer 4 load balancer sends it on to a layer 7 load balancer called Proxygen. This is a system, a reverse proxy. We'll talk a little bit more about it in a bit. But the layer 7 load balancer terminates the connection, and then depending on what the request is, it does different things. If it's static content, it checks the local CD and cache to see if that's cached. If it isn't, we don't hold any user data in the POPs. So it needs to go back to the data centers. So if it's a cache miss or if it's a dynamic request, it goes back to the data center. In the data center, once a cluster is chosen, pretty much the same flow happens. It's almost identical. The hardware is different, but the flow itself it goes through a layer of layer 4 load balancers, gets to a layer 7 load balancer, and then there's another layer of caching in the data centers, where we try to load things from. If we find it there, great. We send it back to the user, caching it along the way. If we don't find it, if it's a static content, we go to the persistent storage, find it, and cache it in both caches back along the way, so future loads can be cached. If it's dynamic content, it hits HHVM, Hip Hop Virtual Machine. This is our web server. It's a virtual machine that runs Facebook, that runs our PHP stack, and we send the response back to the user. Two main benefits of the edge. One's the reduced latency from edge termination, and the other is reducing the impact on the network from being able to cache static content. Talking a little bit about the systems we built to make this happen, Sonar is one of the systems we built to measure latency. So this, in a nutshell, gives you the closeness or latency from different points of the internet to any of our POPs. The way we do this is by piggybacking on existing requests. When you load your feed, you load a lot of really tiny thumbnail images for people's profile pictures. We distribute that really small fraction of it, not significant enough to affect your experience. We distribute a small fraction of it to all of our different POPs. And we stitch together the DNS logs and the web server logs to get an idea of which users behind which DNS server and what the latency from that DNS server is to our different POPs, so we can pick the optimal POP to send them to. Cartographer is the system that does our DNS load balancing. DNS, in a nutshell, when you try to ask for a host name like www.facebook.com, it gets you back an IP address. Cartographer adds intelligence to that by giving you a different IP address based on where you're coming from, and based on what the state of the system at the time is. So it takes into account the data from Sonar in the previous slide, and routing maps for pretty much the whole internet so that we can establish we have an efficient route from the given POP to that DNS resolver. And it also takes into account the health and capacity of our different POPs, so that we're not sending you to the nearest POP, which may be overloaded at the time. Proxygen I alluded to in an earlier slide. This is a collection of C++ HTTP libraries, including an HTTP server. It's not meant to compete against servers like Apache or Nginx, which are really configurable web servers that do a great job. The focus here is really on high performance and the ability to integrate this into your application. It's all open source. You can find this on GitHub if you want to play with this yourself. And we're currently working on mobile Proxygen. So this is the libraries that get linked into your apps on your phone. And when we're able to control both the client and the server implementations, it gives you a lot of power, speed, and flexibility. In particular, on mobile devices, it gives us a lot of instrumentation that we can use to deliver a better networking experience. A lot of the mobile devices have really crappy connections, and this gets us that a little bit more forward. There are a lot more systems we built. It's in the interest of time, I won't be going into details of all of these, but if you want to learn more about any of them, come talk to me, and happy to share more details. So we've been talking a lot about the software. Let's take it a level lower into what the network architecture looks like. Let's start with the POPs, the edge points of presence. So if you peek inside a POP, you're going to see racks of servers running software, load balancing software, CDN caching software, the works, connecting through a top-of-rack switch to routers, which in turn connect to Facebook's backbone, as well as to ISPs through peering and transit links. The problem here is fairly simple. We have different bottlenecks here, which we try to eliminate. Give you an example of a bottleneck. The uplink from the top-of-rack switch to the router is one that was holding us back. So we replaced that with a layer of these fabric switches, which basically eliminates that uplink bottleneck. And it also gives us east-west capacity between racks. Typically, you might hear networkers talk about north-south and east-west capacity. North-south is when there's either user to server traffic, client to server traffic. East-west is when they are between different servers in your own infrastructure. Since this eliminates the east-west bottleneck we previously had, we can combine several clusters into a single large cluster. Now that has some downsides, but overall, it makes these things a lot easier to operate, and it improves your cache efficiency because you've got this single large cache now. We switched from the old architecture to the new architecture in one of our European POPs, and our capacity, our throughput from that POP nearly doubled. The numbers, there's no y-axis on any of these graphs for same reasons as before. There's some things that I'm not allowed to disclose. And now let's take a look at the data center network. In the data center, it's all about volume of traffic. This is a graph which shows the growth of traffic over time within our data centers. The green bar here is machine to user traffic. It looks pretty insignificant here, but if you think back to the first slide, that's over a terabit per second. It's dwarfed by the growth in machine to machine traffic within our data centers. This is what our data center architecture, network architecture used to look like. We call it the 4-post cluster. I can't tell if that's an industry standard term or not, but it's what we called it. It served us well. The gray dots at the bottom are racks of servers connected through a top-of-rack switch to these big cluster switches, which are connected in a ring, and those connect to the rest of the world. It served us well. It got us to over 1 billion users, but now it's starting to show its age. Actually, started to show its age a few years back. Where the bottleneck here is in the size of these cluster switches. We were already buying the biggest the industry had to offer, the most number of ports, highest backplane, and we were still getting constrained. And at the same time, if you look at the mix of traffic within our data center, this is a distribution of the different kinds of traffic. The red is traffic within a rack. The next one is traffic within a cluster but not within a rack. Next one is the data center. And then the last one is like cross data center traffic. We sometimes have like multiple data centers on the same site. This includes both of those kinds. So what you'll observe is that the inter-rack traffic within a cluster is growing. This is actually contrary to a lot of what studies out there are, and it may just be an artifact of the way we build our services in our infrastructure. Nevertheless, this is what we're dealt with, and this is the problem that we need to solve. So we had to rethink things, and we decided to redo it from scratch. For starters, we changed the topology. We rebuilt the data center topology to look like this. If this looks familiar to those of you who are familiar with flow networks, that's because it is. You have like an ingress stage, you have like a crossbars, and you have like an egress. The key part is that we can build this as small as we want and scale this up. So we started with this network where we have an oversubscribed intercluster capacity, and we replaced it with a single data center-wide network. The bottom dot here is the same as the building block that we had previously. It's a rack switch with the rack of servers behind it. The colored dots in the middle are simple infrastructure switches. There's nothing fancy about them. You can get them from any vendor. They're just small and simple boxes. The building block here is what we call a server pod. So you've got about 48 of these rack switches with racks behind them connected to 4 fabric switches. In other words, you have like 48 racks aggregated at 4 aggregation points. The server pods themselves are connected through these parallel spine planes, which is what provides the forwarding capacity between the server pods. You can think of this as like a microcluster. It's a much smaller building block than a cluster. The cool thing here is that you've got several paths between any 2 servers in the network. The fabric provides several equal performance paths. You can have different flows coexisting without competing with each other for the traffic. In terms of subscription, you can build this network out to the level of oversubscription that you want. If you wanted to have an entirely non-blocking network, like one-to-one, you can do it by having enough spines in this. So, and it also deals with failures really well because individual devices and connections are not very important. you can lose cables, ports, components, devices, what have you. The fabric will route around that failure, much like there's a saying about the internet routing around censorship. I think we covered most of the advantages here, but the biggest thing that stands out here is that we can scale this up the way we want it. If we're constrained on bandwidth, we can add more spine switches. If we're constrained on compute, we can add more servers. So going back to our topology, the first piece that we built once we had this topology was our top-of-rack switch called the wedge. The key differentiator for the switch compared to other industry switches is it's got a microserver on board, full-blown Linux environment. If you've heard of the Open Compute project, this is a foundation that Facebook started, but a lot of companies have partnered. It's a collaboration between enterprises and individuals to share technologies, IPs, ideas, code, what have you, that helps with building better data centers. There's a specification for a microserver in there called the group hug. This actually builds using that. Everything in here is off the shelf, doesn't talk any proprietary protocols, and all the specs are in the OCP. So if you wanted to take a closer look, you can. The wedge is now deployed to production and serving traffic. That was it being deployed to production right there. The wedge runs software that's called the FBOSS, Facebook Open Switching System. If it's not so much an operating system, it's a collection of applications that run on top of an operating system. It's got a few different layers, but one of the biggest advantages is it exposes a Thrift API, which is a higher-level RPC programming interface, to the ASIC API, to the lower-level ASIC API. So you can talk Thrift to this and tell the switch what to do on the ASICs. It's got a few other things. It's got OpenBMC is software that controls the BMC, and the biggest advantage is now your software engineers become network engineers because you can treat this like a server. The final piece is this switch called the 6-pack. It takes 12 of the wedge boards that you saw earlier, combines them together, and we deploy these as our the switches further up in the topology, the core or the spine switches. It can be made entirely non-blocking. It's eight of them are front-facing, giving you the ports for your switching, and then 4 of them provide the backplane. It's 40 gig Ethernet, but everything is again modular, so you can switch it out, change it to whatever you need for your infrastructure. Runs FBOSS, so you have the same visibility. To recap, that's the way the data center evolved. We started with the wedge, put a bunch of them together into the 6-pack, built FBOSS and OpenBMC to provide better control. And all of this is part of the OCP. All of this is leading to our vision that the network can be this entirely true open ecosystem that's controlled in software. To bring things to a close before Jim tosses me out, we took a look at what some of the problems are. We looked at some aspects of the solution, software, hardware, both in the POPs and in the data center. The best part is that this is all open. All the software and hardware is out there in the open. Between what you find on GitHub and what you find on OCP, you can recreate everything that we do in our data centers, in our edge, yourself. If you're a researcher interested in research in large-scale systems or innovating in this space, this is a fantastic time to be in the space. There are a ton of opportunities for partnership and collaboration, not just with Facebook, but with many companies in the industry doing a lot of the same stuff. A lot of really cool protocols, a lot of really good papers coming out with key results. And if you're a student or a teacher interested in this stuff, the world just became your textbook, your lab. All of this is out there in the open. We're going to continue to contribute to this, but we're really excited in seeing where the community takes this. And for more information, you can look up GitHub or the Open Compute website, or you can talk to me. That's all I had.
So
two questions.
Yep.
One very specific question, one a more general question.
Mm-hmm.
So is there a tension in Facebook between static and dynamic content? So for instance, statuses at one time could not be edited.
Yeah.
Now they can be. Have they created headaches for you in terms of performance? And the more general question is, so you graduated in 1999? So you've been out for a while.
Yeah.
There's this buzzword called cloud computing. And a lot of the problems that you're solving, Amazon has to solve and Google has to solve. So A, is there some reusable infrastructure where these common concepts are being implemented? And B, conceptually, have you discovered concepts that you didn't learn in school that are concepts that you can teach in class that would help you with cloud computing and distinguish it from what we used to call distributed computing?
Well, that was 5 questions. That's a whole talk in there. Let me see if I can get them in order. Is there a tension between dynamic and static? I don't know if tension is the word I'd use, but we need to address both, and we need to address them in different ways. There are pieces of the product. There are certain product changes which involve significant changes to our infrastructure, and that's when there may sometimes be a tension. I love the folks who build product at our company. They have great vision and ambition, but I've had them tell me like, this is what I want. This is what I want for Christmas. Make it happen. And this is what they tell the infrastructure. And this is, you'll find this echoed across pretty much any company in this business. And that's when you need to like start to juggle your pieces, because some of these things, software we can change. We push code 3 times a day. We can change it in an instance notice. Getting port capacity at a peering site to increase your network footprint, that can take 6 months to sign the contract, and another 6 months before the capacity actually shows up. That's where sometimes it starts getting a little difficult. What were the other things? What did I not learn here? That's actually a really good question. What could have prepared me better for dealing with this industry? There were a lot of things at UNC which prepared me really well for industry, but certain things, especially dealing with failure, for example, is probably the biggest thing that I had to learn for myself in industry. We do fault-tolerant computing. I think I remember doing a course with you where we talked about fault-tolerant computing. Distributed systems course that Don conducted had fault-tolerant computing in there. A lot of that is somewhat academic, and before you can it's one level removed from the reality of what we face in production. In theory, disks don't fail. There's like a mean time between failures just like really high enough that you can pretend they don't fail. But you have enough disks, you have failures every day, many times a day. So the software that you write needs to be able to deal with those kinds of things. And I think this is common to many companies in the space: Amazon, Google, Facebook. Once you get to a certain scale, failure is not occasional; it's all the time.
So are you guys sharing code? How to do that?
Yeah. We share code. More importantly, we share our methodology and our culture. And code's important too. The actual systems we build is important. But there's also a mindset that goes into dealing with failure. A lot of the companies in this space, they don't hide when things go wrong and there's like a major disaster in their site, where it goes down. You actually we have at Facebook we have these things called SEV reviews or incident manager reviews, where it's not people get together, they look at like what happened, how can we detect this faster, how can we prevent this the next time, how can we reduce the likelihood of this happening. Nobody's like, it's not a firing squad, nobody gets fired for taking the site down. So those kinds of places where just encouraging the concept that failure is something you learn from.
Anybody have a question? His name's not for sale.
Why did you feel it necessary to write your own load balancing code, especially for local traffic management?
That's a great question. We used to run load balancers from F5. Now, F5 load balancers work really well for the purposes that they're designed for. Few companies it just wasn't working for us. We were a niche that wasn't their sweet spot. We wanted a lot more flexibility. We wanted to add features. We're an impatient bunch. We wanted to add features really quickly. And when we're able to control the software, when we're able to build that functionality ourselves, it just gives us a lot more visibility into what's going on. It allows us to iterate faster. It allows better integration with the rest of the pieces of our infrastructure. Those are some of the big reasons why we build our own. The mindset is anytime there's something that you can buy or use off the shelf or an open source thing, use it. Compared to some of the other companies that I worked for, I've had lawyers at Intel tell me, like, you cannot use this because it gets us into this whole notion of taint. Facebook, we're an infrastructure company, or at least what I do, it's all in infrastructure. It's all about solving a problem. It's not, nobody's going to tell you, build it here. So to the extent possible, we use stuff that we don't have to build. If it doesn't work, or if we believe there's a lot of value in building it ourselves, then we build it ourselves.
So Facebook, of course, is a business. So when you think about the trade-offs between performance and cost, right? So we talked a lot about performance and speed and reliability here, but not the cost side of it. Is there a driving number around performance that as long as you meet this performance standard, cost doesn't matter? Or what's the trade-off between those two?
It's a trade-off, and actually, I don't know if I'd call it a trade-off. I'll put it this way. Within infrastructure, we are extremely, extremely focused on performance and making use of our capacity intelligently. If we've got servers that are running cold, you're going to get a visit from the capacity engineering folks who will have a chat with you as to, like, why do you need a footprint of 400 servers when you're running at like 90% idle CPU? The load the product places on our infrastructure is constantly increasing. If we didn't make our infrastructure more efficient, you'd get more of like the requests coming in, the kind of demands being made will be increasing. The infrastructure costs will be increasing as well, and we're not going to be around much longer. So our goal is to keep the infrastructure costs flat, even as the weight on the infrastructure keeps going up. So we invest a lot in efficiency.
Well, the main take home for me from this session is that we've had some really good students here. Now let's thank all the speakers.
And the X-Files, the new season begins. So as Jim mentioned, I was here in UNC for my master's after college in India. I collaborated with research with Kevin and Don, and Jim is part of the distributed and real-time systems group. I was I think Michelle and David from the group were in the room. And I used to hack on the FreeBSD kernel, working on the scheduler and the networking stack. And currently I manage part of the networking team at Facebook, focusing on load balancing and transport security. And I've been at a few other places, and with interests that have generally been in the space of networking, distributed system security, runtime environments. And probably the thing that ties together all of these places is almost all the systems that I worked on is in some form out in the public domain, even the stuff that I worked on at Microsoft. So what's in store today? We're going to peek inside Facebook's networking map looks like. We have data centers across the US and in Europe. These are large facilities the size of several football fields. They consume tens of megawatts of power. Everything in there is custom designed for us, by us, software, networking equipment, servers, the works. We also have what are called edge points of presence, or POPs, across the world. These try to bring the network closer to the user, and we'll see more about this in just a second. These are much smaller facilities, typically co-location facilities where we rent spaces, secure cages with racks, commodity hardware, servers, and networking equipment that we buy from vendors, running Facebook software. Much smaller footprint, maybe consume tens of kilowatts of power. Often I get asked, why do we need an edge network? Now, this map is a map of the latency. This is actually round trip time, so twice the latency. from different parts of the world to Facebook's data centers back in 2011. If the numbers are hard to read, darker is bad, and it goes up to about 800.
All right, the final speaker of this session is Arun Moorthy, who was a grad student here back in the roaring 90s. He finished an MS degree here in 1999, and since leaving us, he's been with several companies, Intel, Nexus Systems, Microsoft, and Facebook, where he's now the engineering manager on Facebook's network team. And that's what we're going to hear about today. So
Thanks, Jim.
take it away.
Anybody here did Jim's Comp 202 back in the day? Hey, David. I think you'll probably remember this. One of the most vivid memories I have of UNC, of Jim in particular, is we had these classes really early in the morning, right? Well, early for a grad student. It was like 9 o'clock. And Jim's always has a bounce in his step, but on this particular day, he walks in with a particular bounce, and he goes, "Two things happened which makes life infinitely better," words to that effect. Election season's over, so no more ads on TV. Different kinds of content gets handled. Video is one of the big content types we handle. We handle over 4 billion videos per day. And our user base is distributed across the world. More than 80% of our users come from outside the US and Canada. And all of this needs to be done highly available, highly reliable way. When Facebook goes down, people call the cops. This is a true incident from sometime last year when we had one of our biggest outages in recent times. People were calling 911 to wonder what's going on. This is from the LA, I think it's one of the Southern California Police Department's Twitter feeds. I kid, but in all seriousness, a lot of people use Facebook for many important things in their lives. And when it goes down, it affects them really badly. And we try really hard not to let that happen. Examples might be like coordinating relief efforts during disasters. Facebook use that for, people use Facebook for communications a lot during things like that. Let's start with a primer on what Facebook's global infrastructure. We'll try to see why this is a hard problem, and then we'll look at some aspects of the solution, both hardware and software, both in, on the edge and in data centers. And then we'll see what's next and talk about some, actually I want to hear more about what some opportunities for collaboration and partnership to take this forward would be. I made my best guess as to the technical details in here, but it's really what you want to see. If it's more than or less than or what you wanted to see here, let me know and we can tailor the presentation as appropriate. And stop me with questions along the way. I'm terrible at public speaking. I'd rather do conversation. So what are the challenges for Facebook's network? We're a social network, ever-expanding user base. Last time we checked, it was somewhere around 1.4 billion and counting. They generate a lot of traffic. The numbers here, full disclosure, I'm sandbagging a bit. These are the numbers that I'm allowed to disclose, but you can extrapolate from this if you want. We generate over a terabit per second of traffic through users generating over 10 million requests per second, or RPS.